Okay. Homework 3 is due on Wednesday, and then Friday of this week we won't have a class meeting together. It'll just be a lecture video that day. I'm going down to Greenville to work on the FE exam at NCES. So other upcoming lectures that are going to be recorded, Friday the 16th and Monday, March 25th. Those are the only ones that I know about where we'll just have to have a recorded class video. In each of those cases, I'll still be accessible via email or Teams if you've got questions and need help. I don't normally have office hours on Fridays, but I'm always happy to have you stop by if you've got questions. So does anybody have any questions before we start talking about local losses today? All right. So this equation. What's the name of this equation? Good. James has got it. It's the energy equation. This is actually a little bit different from how I've been writing it, though, on a few occasions in class recently. So this is Where's Waldo thing. Can you spot the difference? How is this slightly different from how I've written it on the whiteboard in recent examples? The location of the elevation? No, that's not it. What is it? HL. What do I usually write? HF. I usually write HF. There it says HL. So what's the difference? That's what we're going to talk about today is what's the difference. Now, remember the way that we use the energy equation is, let's say that we have a couple of pipes that are connected together and we know some information at one of the locations. Like here at location 1, the types of things that we could know there would be its elevation, the pressure of the water at that location. We could know the velocity of the flow through the pipe at location 1. What do you suppose it means in this diagram that this pipe is a small line and that pipe is a thick line? What do you think I meant to imply by that?
Difference in diameter.
That's right. Yeah, difference in pipe diameter. And the reason why that's significant is, so often in the examples until now, I've canceled out V1 and V2. Because if it's the same pipe diameter, then the velocity of the water through the pipe at location 1 and location 2 would be the same. But here, location 2 is in a larger diameter pipe. And so it's not going to have the same flow velocity as location 1. It'll still have the same flow rate, like Q in this pipe will be the same as Q at that pipe, but the V's won't be the same. So I just made that distinction because I wanted to emphasize that we don't always cancel out V1 and V2 because sometimes the velocity will be different at the two locations we're interested in. So here at location 1, we know the pressure head, we know the elevation head, we know the velocity head, let's say. This symbol represents a pump. So what the pump is doing is it's adding energy to the system. So as the water flows from 1 to 2, it's adding energy, and that's why it's on the left-hand side of the equation, is if we're adding up all of the energy at 1, and we want to find out what is the energy situation at 2, we're saying all of the energy at 1 plus the energy that's added by the pump is equal to the energy at 2 plus the energy that was lost as the water flowed from 1 to 2. So that's why H sub L is on the right-hand side of the equation, is that the head losses detract from how much energy remains at 2. And so the three forms that the energy is at location 2 is pressure head, elevation head, and velocity head. And so if there's a lot of head loss between 1 and 2, then there's not very much energy left over to go into these three terms. All right, so that's just to set the stage that the head loss could mean other things than just energy loss due to pipe friction. Pipe friction is a big part of it, but minor losses, or local losses as they're more typically called, include the friction losses and also local losses. For the total head loss, it's local and friction. And so local losses are due to things like pipe fittings where there's an expansion in the pipe diameter, or if the water is going through a bend in the pipe. If it is changing in some rapid way, then it's going to introduce turbulence into the flow and a reduction in energy because of that turbulence. If the water's going around a corner, some of it's going to be swirling around. There's going to be like a countercurrent eddy. You've looked at a stream before. You've watched water flow through a creek, and when water goes around a rock, some of it swings back around, and there can be like a little circle around the backside of the rock. So that's open channel flow, but similar things happen inside of a pipe, that if there's a change, it introduces a disturbance, and any kind of disturbance will be a localized reduction in energy. So here's an equation that shows us how we account for these local losses. There's a K value, which is an energy loss coefficient that we multiply by the velocity head. And the table that you get the K value from will usually tell you which velocity to use. If there is, for example, two pipes with different diameters coming into a junction, it'll tell you whether to use the incoming pipe velocity or the outcoming pipe velocity. You can see this fitting, the two velocities are the same. The flow that comes into the junction is the same flow velocity that goes out of the junction, and so you just multiply the K value by the velocity head, and then that tells you how much energy is lost. And so a relatively smooth and gradual transition would have a lower K value than an abrupt transition, which is going to cause more turbulence and more disturbance to the flow. So same thing with this equation is suggesting that if you have a difference in pipe diameter, and this is a photo from the pipe rack that's back in the hydraulics lab. Do you remember using that pipe rack in 319 last semester? So you've, I think, done some experiments where you looked at differences in velocity through a pipe, and you just multiply the given K value by the difference in velocity, and that's another way to estimate the energy loss due to pipe friction. So the magnitude of these losses are usually less on a system-wide basis than the energy loss due to pipe friction, unless you have a pipeline with lots of fittings and valves, and sometimes, like for example in an apartment network where pipes maybe are going around a lot of different bends before water gets to someone's home. It could maybe be going through lots of different valves. Each floor could have a different cutoff valve, and so there are situations where with a high density of fittings that local losses are larger than friction losses, but that's the exception. And there's lots of different things that can cause these losses. So here's a table from our textbook that illustrates, for example, the energy loss that's going to come from a contraction. Now you'll notice that here in this equation, what they're saying is that you should multiply this by V2, by the outgoing velocity. And that's just simply because that's how these K values have been estimated. So you have to look really carefully at the table you've got to see, have they determined the K values from the inlet or the outlet velocities, because some tables will have it one way, others tables could have it a different way. It's not always going to be necessarily the outgoing velocity, but here in this case it is. And so one of the things that you'll notice is that the difference in diameter is going to give you a different K value. It's not just that there is a contraction and the same K value no matter what the differences in diameters are, but the more dramatic the difference in diameter, typically the larger the K value is. And so, for example, if the outgoing pipe is 20% of the diameter of the incoming pipe, that's what 0.2 means. So 0.2 would be the case if you have a much smaller outgoing pipe diameter compared to the incoming pipe diameter. You've got a larger K value. And the same thing is true if you look at the angle here. That's saying, like, is it a gradual transition which is tapering in such a way that it maybe disturbs the flow less than a really quick and abrupt transition. So an angle of 180 degrees has a higher K value than an angle of 60 degrees because it's going to introduce more turbulence. And so there will be more energy loss as a result. And it looks like more than 5 times as much energy loss. If you an angle of 180 degrees would look basically like you've got one pipe coming in and then just no tapering whatsoever. So this is what the 180 degree angle would look like, and then a 60 degree angle maybe is similar to this. A 60 degree angle would be 30 degrees on each side. Like if we were going to be measuring the angle relative to the center line, it would be 30 degrees, or if we measure it relative to the full angle, then it would be 60. So those are the two trends that I think it's important to pay attention to, is the relative diameters and then how steep the transition is. And expansions, it's a similar story, that there's energy loss due to an expansion because the water that was in some sort of an equilibrium through the small diameter pipe, when it expands, there's going to be a little bit of turbulence as it reestablishes equilibrium in the second outgoing pipe. And so the more gradual the transition, the lower the K value compared to a really abrupt transition. And then the ratio of the diameters also plays a role. Not all of the valves, like a valve is a way of controlling the flow through a pipe or stopping the flow through a pipe. So when you turn the water on at the sink, you're opening a valve. And different types of valves remove different amounts of energy. So you'll notice in this table what this is suggesting of the lowest K value would be for a gate valve that's all the way open. Wide open gate valve only takes out 20% of the velocity head at that location. Whereas a globe valve takes out 10 times the velocity head at that location. We'll look at a difference. We'll look at some depictions of globe valves versus gate valves and why they take out so much energy. A 90-degree elbow takes out more energy than a 45-degree elbow. And so an elbow would be like a rapid change in direction. It wouldn't have any tapering or gradual transition there. If you do have a gradual transition in a pipe diameter, not a pipe diameter, but in the direction, this table at the bottom is suggesting, for example, if you had water that's changing direction, and we've got a certain diameter of the pipe, and then we want to know what's the radius of curvature. So this is the radius, and I guess it's to the center line. So the radius of curvature relative to the diameter of the pipe. So an R to D of 1 is going to be, it's not quite just an angled elbow, but maybe we're trying to round it a little bit. So just with a little bit of rounding, that would be the R to D of 1, and that's saying it's 0.35, whereas a 90-degree elbow was 0.9. So you save a lot of energy just by rounding the edges a little bit, right? You save more energy the more gradual you make that transition. So if we make this a more gradual transition, now that would maybe be R to D of 4, the way I've drawn it. So it gets lower and lower, but the interesting thing is that it starts going up again the longer the transition is. And I think that's partly because the length of the transition is going up, so they may be including a little bit of frictional losses in with the local losses as they're reporting the head loss through the transition. So we have to think about how is the flow being disturbed by the fitting that water's going through. Here is a graphic of a gate valve, one that's closed and one that's opened. The closed gate is just like a piece of metal that's inserted into the pipe. And so the water can't flow through that metal plug. But when you pull the plug out of the way, the water is able to flow through the pipe in the same direction. It's exiting in the same direction that it enters. And part of the reason why globe valves have so much energy loss is because there's a really circuitous route that the water flows through to get through the globe valve, and it's flowing through the plug of the globe valve, which has a really small diameter compared to the incoming pipe diameter. Let me jump ahead to a different figure and then we'll come back in just a minute. Because this globe valve, I think this figure shows it a little bit better, like why there's so much head loss through a globe valve. Remember, the K value is 10, and that's if it's open all the way. Because the water's going through a pipe, and then it enters the valve, it's changing direction, it's going through a tiny little opening. The opening is like donut shaped around this plug that normally would fit down into the valve opening if it's closed. When you pull it up out of the way, there's just a ring of opening that the water's having to flow through. And so it's really contracted. Even when the globe valve is all the way open, there's a contraction inside of this fitting. And that contraction is taking a lot of energy out. The water is losing energy as it flows through. It reestablishes its outgoing flow direction, but it's changed direction several times as it goes from entrance to outlet. And compare that, contrast it to a ball valve. When a ball valve, when water's flowing through the ball valve and it's open, the diameter has just contracted a little bit. We can see that this is flared. You can see that there's a taper there. The incoming pipe diameter is a little bit larger than the water through the ball. The diameter through the ball is smaller, but not compared to the globe valve. So why would anyone ever use a globe valve instead of a ball valve? Any plumbers, DIY plumbers? Explain this. I mean, if the globe valve takes out so much energy, it seems like a bad deal, right? When we lose pressure, that means that upstream you're going to have a bigger pump to overcome the effect of the valves. So you're losing pressure in the house. You know, it means the water comes through the person's shower head with a lower flow, and nobody likes low flow. Yeah?
Is the globe valve, is that the type of valve they use for like a pressure regulator that comes into a house?
Well, any valve when it's partly closed is going to reduce the pressure downstream. But it does have something to do with pressure. Like water could leak around a ball valve. Like water can leak around the edges of the ball. So it's not as watertight as a globe valve. And so sometimes people go a little nuts if their sink is dripping, right? So you can't just have the lowest K value as your only parameter for choosing which valve works in a certain fitting. You want it to be the acceptable combination of water tightness and minimizing energy losses. So if I go back to here, we were comparing so gave valves, we talked about that's just a pipe that has a plate that can swing in. We've looked at a globe valve in some detail. What's the K value for a closed globe valve? Like infinity. That's the reason why water isn't flowing through the system. If the valve is closed, there's so much head loss that the water is flowing zero. So a closed K value, that'd be a good trick question. A check valve or a swing valve is one that's often put in place in sewer applications so that it allows water to flow one direction but not allow the water to flow the other direction. So like if you had in your basement a drain going from the foundation drain to the sewer that's out in the road, you'd probably put a check valve in case the sewer backs up so that sewage doesn't get into your home. The city of Huntington about 10 years ago had a real problem with several neighborhoods in town where sewage was just constantly going into people's basements, and I think they've largely solved that by installing a lot of check valves. This is showing the K value for water coming out of a tank. So this is just showing, like if you had a reservoir and a pipe coming out of a reservoir, the K value that would apply for different configurations. And so if you have a mitered edge versus, in the case of a pipe protruding into a reservoir, the K value would be higher if it's protruding in. If you have a gradual tapered transition, like you can see this is more rounded, then the K value goes from 0.5 to as low as 0.04. And then if you have the water flowing at an angle, then this is suggesting that you could determine the energy loss coefficient as a function not only of it being an abrupt transition, 0.5, but then some additional losses having to do with how steep that angle is. Okay, we've looked at these two valves. One thing I want to point out is what it looks like when you go to a fitting manufacturer. They can post their K values online, and it also depends on the diameter of the fitting. So we've talked about how one of the factors is how smooth the transition is, of course, but also they have different K values for different pipe sizes. And so they're saying their 6-inch swing check valve has a K value of 1.5, whereas their 1/2-inch swing check valve would have a K value of 2.7. So you have to go to the manufacturer of whatever fitting you're using and see what sort of published data they have. So tables like this are available from most providers. Okay. Well, let's get some practice accounting for all of the head loss. We've done a few problems where we were accounting for only the energy loss due to pipe friction, but here let's account for both. And we know some things at location A. You can see that the pressure is defined at location A. We know the elevation difference between A and B. It says that in the problem statement. It says that they're 1 kilometer apart, and I am going to ask that we use the Hazen-Williams equation to estimate the pipe friction. Remember that there's two different ways that we can often apply to calculate the energy loss due to pipe friction. There's Darcy-Weisbach, which is more complicated but more accurate, and Hazen-Williams, which oftentimes is good enough. And this is one of those cases where we'll say Hazen-Williams equation is good enough because what we're really trying to do is get some experience applying the local losses. So you'll see it's saying that there's a pipe bend, and the K value is given for the pipe bend. There's a globe valve with the K value, another pipe bend, and then we want to find out what's the pressure downstream at location B. Now this problem is pretty simple. If I wanted to make this problem a little bit more complicated, what I would do is I'd have two different diameter pipes. Like if I had one pipe diameter going into the valve and another pipe diameter coming out of the valve, then that would complicate the problem in several ways. It would make it so that you can't now just cancel out V1 and V2, which you can do if they are the same diameter. You will be able to do that in the energy equation, cancel out V1 and V2. But if they were different diameters, you wouldn't be able to. And another thing that it would do was you'd have to calculate the head loss due to pipe friction in two different pieces. Like if you had small diameter, large diameter, remember diameter is one of the terms in the Hazen-Williams equation. So you'd have like the head loss through the first pipe, and then the head loss through the second pipe would be like a separate calculation. And then the same thing is also true, remember, of local losses. Because local losses, you multiply the K value by the velocity head at the fitting. And so if it was one velocity here in this first pipe bend, then you'd need to multiply whatever the velocity head at that location is by the K value. But then this other one would have a different velocity. But this is a simple problem. So what you can do is you can just add together all the K values. See how this says the sum of the K values? Since all of the velocities are the same at those three locations, you can just sum the K values together and multiply it by the velocity. But this is just a warning because in the homework or on an exam, it could be the case that you've got different velocities due to different pipe diameters. And when that's the case, you need to keep the pipes separate, keep the velocity heads separate. You can't just aggregate everything together, summing up all the K values, if you have different velocities through the system. All right, so that's enough of a background. Let me pause for a second, give you some time to calculate this one. We're trying to find out what's the pressure at B. So there's energy loss. There's pressure change because of elevation difference. There's both the friction component of the energy loss. There's the local component of the energy loss. Tell me, what is the pressure at B? If I was going to make this an exam problem, I wouldn't have given you the velocity straight away. I would have told you the flow rate and made you calculate the velocity. And if I was going to make this an exam problem, I already told you I'd give you two different diameters. So you'd have to calculate two different velocities. But aside from those two changes, and I think this is a pretty fair representation of what you can expect on the first exam, the type of problem. So let's look at the solution. I've been circulating around, and I think in most cases people are on the right track. If not finished, they're headed in the right direction. So I think it's important to let your solution breathe. You know, don't cram it together in too small of a space. We do these calculations and solutions. It's a form of communication. You know, homework, you're just trying to get it over with. I understand that. But like when you graduate and are practicing, you are summarizing a mindset and a problem-solving process to other people on your team. You have to maybe have these notes available for yourself so that you remind yourself years later, in some cases, what you were thinking. So you want to be as expansive as possible. You really want to show the equation, the substitution, including the units in the calculations. Doing that will help you avoid mistakes. But the point is paper is inexpensive, so feel free to use plenty of it when you solve your assignments. What we've done is just at the first kind of summarize this scenario. What we're trying to do is find the pressure at B. So the friction losses, 43.1 meters. The local losses, in this case, we could just sum up all the K values because at each of those three locations, the velocity was the same. So the local losses are less than the friction losses, but they're not insignificant. You know, sometimes we call them minor losses. You'd get a pretty different pressure reading if you just ignored them completely, if you only accounted for the friction losses. All right, so what we're going to do is we're going to substitute those into the energy equation. So the energy equation here, we know the pressure, the elevation, the velocities. We know the elevation at 2. We know the head losses. The only unknown in this equation is going to be P2. So rearranging that equation to solve for P2, we've got the unit weight on the outside of this expression, and then on the inside, we're saying the energy at 1 minus all of the things that are reducing the energy between 1 and 2. So what's reducing the energy between 1 and 2 is an increase in elevation, the friction losses, and the local losses. So those three things, elevation increase, friction losses, and local losses, are going to be taking away from how much pressure there is downstream. Okay, now we can substitute in the numbers. I've written the unit weight in terms of kilonewtons per cubic meter. We could have also solved this just by multiplying it by newtons per cubic meter. You know, so 9810 newtons per cubic meter is the same thing as 9.81 kilonewtons per cubic meter. So it's not wrong if you wrote 9810 newtons per meter cubed. But I think it is important to write the units with each step of the problem. I think in the long term it's worth the investment. So here you can see I've come up with this intermediate distance, 66.259 meters. That's how much head there is at location 1. That's the amount of pressure head at 1. We've got 66 meters of pressure head, and then all these other things are taking away from that pressure head, and what's left over will be related to the pressure at location 2 downstream. So it should be 21.3 kilopascals downstream. So I like here having all of these things showing because it shows you the relative magnitude of each. like how important is each one of those things that's reducing the pressure? Because what if they said, well, that pressure's too low? And in fact, there are rules on how low the pressure in a domestic water system can go. Like even in an emergency, like when there's a fire in a neighborhood, your pressure shouldn't go below 140 kilopascals. And that's partly for convenience and so that water can still flow to the fire hydrant, but it's also for water quality reasons, because if the pressure is too low, then there can be a situation known as backflow, which is somebody could open up a valve and the water actually enters the pipe network instead of exiting the pipe network. Or if the pressure's too low and the water line crosses a sewage line that's leaking, then you could have contaminated water getting into the water line if the pressure's too low. So there are limits, and so this is below what we'd usually say is the emergency lower limit of 140 kilopascals. So part of the reason why I like to express these each individually is then that tells us what we could do to change the situation. Like we can't often change the elevation of things. You know, we're trying to get water up onto that hill. We can't make the hill lower. So maybe the Z2 isn't something we can change, but we could look at this and say, well, we're losing most of this energy loss due to pipe friction. What could we do to reduce the pipe friction? We could get a little bit less energy loss if we had a smoother pipe, but by far the biggest thing we could do is by making it a larger diameter pipe. And if you had a larger diameter pipe, then let's look at the equation here. If you had a larger diameter pipe, then the velocity would be lower, so that reduces V, which is in the numerator, and it increases D, which is in the denominator. So it has a twofold effect. If we have a larger diameter pipe, we're going to have a big reduction in the energy loss due to pipe friction. And as a plus, that larger diameter pipe would reduce the velocity head, and so the local losses would be smaller as well. So we could change in different fittings, and that maybe would help, but we'd have to know, well, how much extra pressure are we looking for? So that's just a little bit of the mindset that would go into design. Like if this is analysis, where we're just finding out how much pressure is there downstream. But then if someone tells you that's not enough pressure, you have to design the solution, then you'd look at this and say, well, our solution has a couple of possibilities. We could increase the pressure at location 1, potentially with a pump, or we could reduce the rate of energy loss due to pipe friction, or we could reduce the rate of energy loss due to local losses and fittings. Any questions on that example? All right. Let's get some practice with the Moody diagram. I've got a couple of problems I'd like you to solve, and if you've printed the notes, you may already see the answers. Don't look ahead at the answers, okay? I'm going to give you a piece of paper. Don't peek. We're going to calculate the F value for two cases. One is with water. So I've given you the kinematic viscosity of water flowing through a 45 millimeter diameter wrought iron pipe at this flow rate that's given. Determine the F value. And then the other one is kerosene. Different diameter pipe, giving you the case of S values. We may not have time to get through both of them, but I think we definitely will have time to get through the first of them. Find out what F value applies for water flowing through this pipe, and we need to get some practice using the Moody diagram. You the solution process here. Up on the whiteboard, I've written that the first thing we do is determine the velocity. So we know the flow rate, 0.2827 liters per second. We have to divide that by 1,000 to get cubic meters per second. Divide that by the area of the pipe. If it's a 0.045 meter diameter pipe, then that means it's an area of 1.59 times 10 to the minus third meters squared. So the velocity through the pipe is 0.177 meters per second. Calculate the Reynolds number. It's 8,000. the Reynolds number is 8,000, and the relative roughness, if the K sub s is 0.045 and the diameter is 45, then the relative roughness is 0.001. So what we do is look for the point of intersection with the relative roughness. Here in red, I've overlaid in red on top of the curve that follows 0.001 and intersected it with the Reynolds number of 8,000. So we're in this transitional zone where both the relative roughness and the flow conditions together account for what the F value is. So the F value that applies here is 0.034. In the second problem, I hope that you'll go through the calculations and get the extra practice. Let me jump ahead and show you what the answer is. For the second one, we're going to get that the relative roughness is 0.004, 0.0004, and then that is a Reynolds number for the flow conditions that are described of 1.5 times 10 to the 7th. So we are in the rough turbulent zone, where it's only the relative roughness that affects the F value. That it could be even higher Reynolds number, but the F value would be the same. So 0.016 is the F value for this second case with kerosene. All right, we are out of time. Remember that your next homework assignment, number 3, is due on Wednesday. So I'll see you then.